So we're going to start Module 7, Section 7.2, Sample Proportions. So our learning objectives for this section are to find the mean and standard deviation of the sampling distribution of a sample proportion, determine whether or not it is appropriate to use the normal approximation to calculate probabilities involving the sample proportion, calculate probabilities involving the sample proportion, evaluate a claim about a population proportion using the sampling distribution of the sample proportion. Okay, so this is a little activity. If you would like to go through it, you can open up those PowerPoint notes. You'll have to go to this website and feel free to look over and do that and answer these questions as you're going through. Okay, so the sampling distribution of p hat. How good is the statistic, remember, p hat as an estimate of the parameter p? The sampling distribution of p hat answers this question. Consider the approximate sampling distributions generated by a simulation in which an SRS of Reese's Pieces are drawn from a population whose proportion of orange candies is either 0.45 or 0.15. So after that Java applet that you opened, you can kind of look. So here, if you were to do one, 0.45, and I don't know why, sometimes they use the pi symbol for the population parameter, but we're going to use p. Okay? So what do you notice about the shape, the center, and the spread of each? Okay, well, the shape, it looks pretty normal. When your n increases, it's going to get more and more normal, and as the population proportion increases as well. The center, well, what did you notice? That the mean was just the p-value. This makes sense because the sample proportion is an unbiased estimator of p. And the spread, the standard deviation gets smaller as n gets larger. So that standard deviation is going to depend on both n and the p. So this is really, really important to know, that your standard deviation gets smaller as n gets larger. Okay? So there is an important connection between the sample proportion, p hat, and the number of successes, x, in the sample. P hat is going to be the count of successes in the sample divided by the sample size. So, if you want to get these from Chapter 6, we learned that the mean, or Module 6, we learned that the mean and the standard deviation for binomial looked like this. But now, if we have that p hat is going to be x over n, then we're going to have 1 over n, basically, times x. So we're just multiplying the random variable by a constant 1 over n. So if I multiply np times 1 over n, I would get out p, which is what we saw. Now, the standard deviation, again, you're just going to take what we saw from the binomial and multiply by 1 over n. And here, if I distributed that inside the radical, I'd have to put in an n squared. And then we could cancel out one of those n's, and this would be our simplified formula. So as the sample size increases, the spread decreases. You can think about that. As you have a bigger and bigger number in the denominator, it makes that standard deviation, what it equals, get smaller and smaller and smaller. Okay? Bigger number in the denominator, smaller number overall. Okay, here you can see several examples when your n sample size increases, your spread, standard deviation in this case, decreases. So it's going to make the graph skinnier and higher when you get a smaller variation, because remember, the area always has to be 1. So you're not changing the area under the curve, you're just changing that shape, the variance here. Okay, so this is what we just had. Okay, how to find the mean. It's just going to be the p, the standard deviation, p times 1 minus p, so the success times the failure, divided by n radicaled. And we need to make sure that the 10% condition is satisfied here. And I like to say 10 times n is less than or equal to n. And as n increases, the sampling distribution of p hat becomes approximately normal. So before we perform any of those normal CDFs, if you remember that, any normal calculations, we have to check that we also have these conditions met right here. So this is for normal. Okay. This is to make sure that we are independent. This 10% right here, okay? This is to check that we are independent and that we can apply that standard deviation. The n times p greater than or equal to 10 and the n times 1 minus p greater than or equal to 10 tells me I have at least 10 successes and at least 10 failures. If I have 10 successes and 10 failures going on, then I can say that we can use normal calculations. Okay, so the population distribution, even if the population distribution is skewed, as n gets larger and larger and larger, the sampling distribution, sorry about that, becomes more normal. Okay, so even if your population was skewed, your sampling distribution can be normal if your n is large enough. How large? Well, if you're dealing with proportions, it's n times p. If you're dealing with means, which we'll get to, it's 30 when you have means. And if you're dealing with proportions, you have to have n times p greater than or equal to 10 and n times 1 minus p to be greater than or equal to 10 before we can say, yes, it's going to be normal. Okay? Here you can just kind of see what's going on. Larger the sample size, the more normal. Okay? And as the sample size increases, the spread decreases, so it's going to get skinnier. So these up here were some sample populations. And then, or sorry, were the populations, and then we did some samples going on. That's when we did 2, 6, 30. You can see it's going to become more and more normal. All right, so if we want to summarize again, that we're going to let the mean just be p. The standard deviation is the success times the failure proportion divided by n, all square rooted. And we can only take the standard deviation if our 10% condition is met. And if we want to talk about the shape or anything with the approximately normal, then we're going to have to show n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. And again, this is for proportions. Just a visual, so you get it in your head. So let's do an example. Suppose a large candy machine has 15% orange candies. Imagine taking a simple random sample of 25 candies from the machine and observing the sample proportion p hat of orange candies. What is the mean of the sampling distribution of p hat and why? Well, the mean of the sampling distribution of p hat is just going to be our p, and we said that that was equal to 0.15. Okay. Find the standard deviation of the sampling distribution of p hat and check to make sure the 10% condition is met. So let's see. I had 25. So 10 times 25 would be 250. Is that less than the population of all of those candies? Very, very likely. Okay, so let's find that standard deviation. The mean sub p hat, or sorry, the sigma sub p hat, the success times failure over the amount, which is approximately 0.0714. Is the sampling distribution of p hat approximately normal? Well, in order to answer that, we're going to have to check n times p and n times 1 minus p. So n times p is n was 25 times 0.15, and n times 1 minus p would be 25 times 0.85. Well, let's see, this one equals 3.75. We don't have to go any further. This is not greater than or equal to 10, so no, it is not going to be approximately normal. D, if the sample size were 75 instead of 25, how would this change the sampling distribution? Well, would it change the sample mean? So the mean would stay the same. What about the standard deviation? What would it do? So here, if we increase the number we're dealing with, it's going to get smaller. And in fact, you can go put that in and see it's going to be approximately 0.0412, which is smaller. And what about normalcy? Is that met? So here, if I did 75 times 0.15, I got out 11.25. And 75 times 0.85, I got out 63.75. So the shape is definitely going to be different. So the shape is approximately normal, because those are both greater than or equal to 10. And there's just me writing up stuff. Okay, here's another example in the game of Scrabble. Who doesn't love Scrabble? Each player begins by drawing 7 tiles from a bag containing 100 tiles. There are 42 vowels, 56 consonants, 2 blank tiles in the bag, which we all want. Giovanna chooses a simple random sample of 7 tiles. Let p hat be the proportion of vowels in her sample. Is the 10% condition met in this case? So let's see. I wanted to do, how many are we doing? 7 times 10 is going to be 70, which is less than the population of 100. So yes, we are good. Okay. Is the normal condition met in this case? Justify your answer. So let's do n times p, which would be 42 out of 100. And I got 2.94. Ah, that is not greater than or equal to 10. So no, it is not. We don't even have to check the n times 1 minus p. Hanging in there, doing good. All right, the university is concerned about the academic standing of its intercollegiate athletes. A study committee chooses an SRS of 50 of the 316 athletes to interview in detail. Suppose that 40% of the athletes have been told by coaches to neglect their studies on at least one occasion. That's horrible. What is the probability that at least 15 in the sample are among this group? All right. So let's go see if we can find the mean, the standard deviation, all of that fun stuff, and then we can do our normal CDF. So let's see. In order to get my standard deviation, I'm going to have to check the 10% rule. So let's go check that. So how many were in my sample? 50 times 10 is 500. That is not less than the whole population of 316. So my 10% rule, we are not independent. So we cannot use this guy, okay? We cannot go and find the normal CDF. All right, let's do one where you can now. All right. About 75% of young adult internet users ages 18 to 29 watch online video. Hey, that's you. Suppose that a sample survey contacts an SRS of 1,000 young adult internet users and calculates the proportion p-hat in the sample who watch online videos. What is the mean of the sampling distribution? Okay, so that's just your p, which was, they told us, 75%. Find the standard deviation of the sampling distribution. And we have to make sure that the 10% condition is met first. So I'm doing an SRS of 1,000 times 10, which is 10,000. And I'm going to guess that the population of young adult internet users is definitely greater than this. Okay? Young adult internet users. So let's see, sigma sub p-hat, so that standard deviation is going to be 0.75 times 1 minus 0.75 over n, which was 1,000. And that is approximately 0.0137. Is the sampling distribution of p-hat approximately normal? And check that the normal condition is met here to see. So let's see. N times p would be 1,000 times 0.75, which is 750. That's good. And 1,000 times 0.25, which is 250. So both are greater than or equal to, here let's just use the symbol, make life a little easier. Both are greater than or equal to 10. So yes, it is approximately normal. So here's the fun question. If the sample size, oh, that's not what I wanted a normal one. Okay, anyway, so if the sample size were 9,000 rather than 1,000, how would this change the sampling distribution of p-hat? Okay, so how would it change the sampling distribution? So we're still going to be normal because we're getting bigger here. We already showed that something smaller was normal. We're going to have the same mean. What about sigma? What's going to happen? The spread will decrease. You'll have less variance. Okay? Sigma sub p sub hat is actually smaller. It's going to be around 0.0046. So it's going to go from something like this to something like that. Okay? All right, we'll get to the normal ones. Don't worry. All right, here we go. Using the normal approximations. Okay, so if we have all of those conditions met, we can do the normal CDF. If you remember, when we do normal CDF, you're going to do the start, the end, the mean, and the standard deviation. Well, you can't do that unless it's normal, first off. So you have the n times p and n times 1 minus p that are both greater than or equal to 10. And that you can use the standard deviation using that 10% rule. Okay? Okay, so, and sorry, don't forget, this is not enough work. You have to either draw a graph or state what you're doing within the normal CDF. Okay? like finding the area under the curve from blank to blank. So, a polling organization asked an SRS of 1,500 first-year college students how far away their home is. Suppose that 35% of all first-year students actually attend college within 50 miles of their home. What is the probability that the random sample of 1,500 students will give a result within 2 percentage points of this true value? So, let's start by first finding the mean. All right, so our mean here is just going to be what they told us of 35%. Okay, what about the standard deviation? Well, I need to check the 10% rule before I can do the standard deviation. So let's see, if our n is 1,500 times 10, that gives me 15,000. The population of first-year students is definitely bigger than that. Okay. So let's see. Let's go find it then. Sorry, that was just checking to see. So this is actually now the equals. Okay. So I could do radical 0.35 times 1 minus 0.35, all divided by n. And let's see if it is normal. So let's see, n times p and n times 1 minus p are both greater than or equal to 10. So yes, it is normal. So what's the question now asking for? It wants to know that it's within 2 percentage points of the 0.35. So I'm going to do a normal CDF, and where would I start? What's 2 percentage points below 0.35? That would be 0.33, and 2 percentage points above 0.35 would be 0.37, and then my mean, and then my standard deviation. And if you want to put the rounded in there, go out a few decimals. I'm going to put the exact in, okay, so we can get an even better answer. And that's approximately 0.896. My point kind of got smeared. What did I say? 896. Okay. Now, again, this is not enough work. You would have to draw something like this on the AP exam, or tell me the area under the density curve from 0.33 to 0.35 with a mean of 0.35 and a standard deviation of whatever that was, 0.35, 0.38 over 1,500. That's radical. Has an area of 0.896, of approximately 0.8936, 0.896. Okay, so that's pretty good. That's almost like a 90% probability here that you're within 2 percentage points. All right, see if you can do this next example. And you can pause me, and I'm going to go ahead and show you the answers. and see how you did. All right, so section 7.2, sample proportions, just a little summary of what we did. And next we're going to do some means. So this was all about proportions. We're going to do means next.